I do believe, yes, we are recording, and we shall see what becomes of our session. You guys got one? Thank you, Ben. All right. Now, as you can see up on the projector, we have the topic of the day. This study session is going to be dedicated to writing justifications, explanations for the exam. So, on the test, you've seen already some of the review problems we've done. It says, justify your answer, explain your reasoning, explain the meaning of a definite interval. We saw that on some of the questions we did today. The total number of gallons of water that exited the pipe, that type thing. So, as is this, the author of this document gives us, it's the way to approach the question: identify the theorems or definitions that might be used. To identify the theorem, you need to know the hypothesis and conclusions. The wording of the question may mimic the conclusion of the appropriate theorem. So, let's think in that sense, if the wording of the question may mimic the conclusion of the appropriate theorem. Today we saw one question that said, can we guarantee the fact that f prime of x will equal 0 for some value on the 24-hour interval? Something of that phrasing. Well, so the conclusion that we're trying to figure out is, can I prove that the derivative will be 0? And we remember back, was there a theorem that ended that way? So Rolle's theorem guaranteed the existence of some c on the interval AB such that f prime of c equals 0. So knowing the wording of our big theorems is going to be key to us. All right. And as this states, some of the theorems that are most often used are going to be using a first derivative test, which is going to calculate what for us? Or what can we use first derivative tests to guarantee we know it's true?
Extremes. Relative extremes.
Relative extrema. The first, and now, Jake, you were saying it's going to increasing, decreasing. Yes, first derivative test is going to be able to show that we're changing from one interval of increasing to another interval of decreasing. And therefore we can say, yes, I have a maximum, or yes, I have a minimum. What does second derivative test use to show?
Concavity. Points of inflection?
No. Not concavity, not points of inflection. It uses concavity to guarantee the existence of a what? Of an extrema. Yes. Second derivative test guarantees the existence of a max or min because second derivative test takes the critical numbers from the first derivative and you test them in the second derivative. If we had a spot that has a minimum, my first derivative is 0, and I can show by second derivative test that at that critical number I'm concave up, thus I have a minimum. That's what a second derivative test is. Both of these test for extrema. And this other guy, a candidate's test, it says this is a combination of the first derivative test and the extreme value theorem. A candidate's test is testing absolute extrema. What's the absolute maximum of the function on some interval? What's the absolute minimum of some function on the interval? So basically, you're going to find your candidates, which are your critical numbers, and the endpoints of the interval. And if you're trying to find the absolute max or the absolute min, you're looking to find out which has the absolute biggest y-coordinate and where is the absolute smallest y-coordinate. So you get your candidates, all your critical numbers, and your endpoints, and you put them back in the original function. And just compare y values. The very biggest y value is the absolute max. The very smallest y value is the absolute min. Now, what do you have to know for sure about the function to be able to use that guy? Go ahead, JT.
That is continuous.
Right, that is continuous. Right. That is going to be continuous because you got to show that from the left endpoint, let's say it was a y-coordinate of 2, to the right endpoint that was a y-coordinate of 7, then you know you're continuous everywhere in between. That's a definite must. Because if you had a vertical asymptote in there, then you can't guarantee 7 is your maximum because you might shoot off to infinity. All right. extreme value theorem, intermediate value theorem, mean value theorem, all these guys are going to be ones that require you to use some sort of a statement to justify. Let's see what else we got here. All right. Now, and here's the key. So once you kind of know from the prompt what theorem you got to use, then you've got to make sure that the hypotheses are met. In other words, when it says on, like, say, mean value theorem, if f is continuous in the closed interval AB and differentiable in the open interval AB, that's our if. You've got to show somehow that you know that those conditions have been met. Usually they tell you h is a twice differentiable function. You know you're continuous and differentiable right there. So all you got to do is say, since h is differentiable or twice differentiable, then, right? Then that allows us to say or calculate that we know that some c exists such that f prime of c equals f of b minus f of a over b minus a. Now we'll see that in action here in a minute, but today I've been throwing those out at you to hopefully make you go, oh shoot, I don't remember that. So we better get it back in your head, right? All right. So it says this may require some computations that you show on your paper. Okay. Show that the slope of the curve, the instantaneous rate of change, is going to be 4 at some time on the interval 0 to 50 or something. Well, you just got to show that there is some average rate of change that has a slope of 4. And then you can say, tie these together with a short sentence, therefore by the mean value theorem we are guaranteed some time t between 0 and 24 or whatever, that the instantaneous rate of change will be 4. Okay. Now, I'm not sure where this packet goes. They jump right into some functions. Okay. This practice number 1, 2008 BC5. Now, if you flip into your packet, let's see, 1, 2, 3, 4, 5, 6, 7, 8. All right, well, the 9th page is the BC 2008 question 5. But before we go there, let's put up some stuff in here that this packet gives you. I'm going to switch over to the document camera real quick. Alright. I am, oh goodness, where am I at? 1, 2, 3, 4, 5. I'm on page 6. Page 6 of your handout. This just gives you, in fact, Nicole, you asked today, I think in class, which ones do we got to know? This is it. These are the big guys. You need to know intermediate value theorem. You got to, if you have the theorem in your head, then you can reference it and talk about it on the justification. All right. Now, the wording that this author uses might be a little teeny bit different from the wording our book used exactly, but it's the same stuff. You know, if you open your book and look up one of these, it might be worded just a tiny bit different, but it'll say the same thing, or communicate the same thing. Intermediate value theorem guarantees the existence of some function value between any other two function values if you know the function is continuous. Extreme value theorem, I won't go through and read every one of them, but these are the big guys we got to have. Intermediate value theorem, extreme value theorem, mean value theorem, and Rolle's theorem. Now, essentially we've said that Rolle's theorem is just a special case of mean value. So you can prove anything Rolle's theorem with mean value. It will suffice. So if you want to just memorize one for sure, it needs to be mean value. But it'd be nice to have them both. Because we saw the question today that was easy to answer since we knew f of a equaled f of b from that table of data in class today. Okay, so we got those. The next page, increasing, decreasing theorem. Basically, all that says is if your derivative is positive on the entire interval, you're increasing on the entire interval. If your derivative is negative on the entire interval, then you're decreasing on the entire interval. And remember, intervals of increasing and decreasing are closed intervals. Intervals of concavity, no, they're open. Intervals of increasing and decreasing, you communicate them as closed. First derivative test, we talked about that earlier. Second derivative test, again, both of these will give you what they call either local or what we call the relative max or relative min, local max, local min. First and second derivative tests guarantee extremis. Okay. That basically gives you a list of the big ones we got to have.
Is there any like where they talk about like average value of a function or those kind of?
Well, the average value of the function is another theorem we got to use. The average is not included in this list because average value of the function is just going to calculate an answer for us. What's the average rate of water flowing out of the pipe? Well, we find the average value of the rate of water function. But it's not going to be a question that's asked, explain your reasoning, justify your answer. Your justification for that is showing the integral 1 over b minus a times the integral from a to b of whatever function you're doing. So there's no explaining your answer on that one. The ones we had listed here are the ones that require some justification. So let's take a look. The very next page is BC number 5 in the 2008 exam. And don't let this bother you because this is a BC question. Remember, AB has lots of, the BC test is a lot of AB material. So for you AB students in the room, no biggie. Okay, so let's get our brain around this question. The derivative of a function is given by this x minus 3 times e to the x for all x greater than 0. And f of 1 equals 7. Now, as we just read that and pause, does anything stand out to you of what they've given you? They've given us the derivative, and what else?
A point.
A point. How do you think those two might be connected?
Tangent line.
Well, I might use it for a tangent line because I can calculate the slope here, and I'll have a point. Maybe I can use it for that. That's good. What else? Right. That's where my brain went. We might be asked to integrate this, and then I can use the 1/7 to find my plus c. I might use it to find some other function value if they give me some more information. We'll see. But here's the first one, the part A. This is a justify your answer. So let's see what it's asking for. The function has a critical point at x equals 3. Okay. Now, what do you mean critical point? What's that mean to us?
Either max or
Where y
min.
equals 0.
Excuse me?
Where it equals 0.
What's the it?
The derivative of.
Okay, yeah. Well, the derivative is 0 or maybe
Undefined.
undefined. Okay. We quickly can put 3 into our derivative function and we can see it's going to be what value? What?
0.
Yeah, it's going to be 0, right? So, okay, my derivative is 0. And they're telling me it is a critical number, so I didn't have to solve for that. At this point, does the function have a relative minimum, relative maximum, or neither? Justify your answer. Okay. Now, typically I'd have you guys work through this, but time-wise, we're just going to crank here. Here's the correct answer. Now, note how they put their solution there. If we were going to work this guy out, f prime of x equals x minus 3 times e to the x. I'm going to write that up. Smell, Nicole, you're on camera.
Oh, that's awkward.
All right. Let's see, x minus 3 times e to the x. Let's put this up here. Now, here we go. That's what I was looking for. Okay, now this one was, oh shoot, what was it? 2008 question 5, so a non-calculator question, right? So I couldn't just graph this and look at it, which wouldn't be justification enough anyway. If I want to find this guy, and I'm told that x equals 3 is a critical number. All right. How would you start trying to justify that this guy's going to give me a max or a min? First or a second derivative test, okay? They gave me the first derivative. If I'm going to use the second derivative test, I've got to take the derivative of this. Which do you think is the safer route, first or second derivative test? First, because they gave it to me. If I take the second derivative test, I might mess up the derivative. I don't think we would, but you might. Okay, so with first derivative test, what am I trying to set up? Intervals. Okay, what would my intervals be? Negative infinity to 3. What else? 3 to infinity. Okay, well, I disagree. Go, JT.
Negative infinity to 0 and 0 to 3 and 3 to infinity.
No,
Oh.
I don't want the negative infinity at all. That's the issue. Read the prompt again a little closer. The prompt says the derivative of the function is given by this derivative for x greater than 0. So this derivative is good, but only for x is bigger than 0. So I wouldn't want to take something like -7 and put it in here. I might get some bogus, weird thing that doesn't fit. So I don't want to go negative infinity to 3, but I want to go 0 to 3. And then I can go 3 on to infinity. Okay, got my test intervals. Now what are we going to do?
Fine.
Test.
I'm not going to plug anything.
We're not plugging.
Sub values. Plug and chug.
Plug and chug.
Throwing hurts too. Hey, now, never plug in calculus class. All right, we're going to substitute. What am I going to say? Okay, no, not -1.
Oh. 1.
1. Okay, let's substitute 1, something in our interval. All right, into my derivative, I'll test a 1. And of course, that's going to give me 1 minus 3 times e to the first. It's a non-calculator answer, or question rather.
You know it's going to be positive though, so it doesn't matter.
Decrease is going to be negative.
Oh wait, it's going to be negative, yeah.
Yeah, this one is negative, okay. And basically, it's going to be negative 2e, correct?
Yes.
All right, so it is negative. All right, so that tells me my first interval is doing what?
Decreasing.
Decreasing, okay. So I can go up here. This is notes to myself, so to speak. What am I going to do with the second interval?
Put in a 10.
Substitute in a 10, okay. Test it at 10.
That doesn't make a difference.
10 is a number on that interval, we can see. So I'm going to have 10 minus 3 times e to the 10th. That's going to give me 7e to the 10th. I don't have any clue what value that is, but it is positive. Therefore, my second interval is doing what? I mentioned increasing. All right. Now, what have you convinced yourself is going on at x equals 3? Relative minimum. Okay. So you're going to state right now, relative minimum at x equals 3. Okay, we got that. Now, justify your answer. This is what we're here for tonight.
Because I just showed you.
No, not because I just showed you. Because you didn't just show me.
Oh, no.
All you showed me, really and truly, in terms of the AP Reader, is that you know what the value of the slope of the curve is at 1. And you know the value of the derivative at 10. That's all you've told me you know. All right, JT?
You had your global.
Global argument.
This is that idea of a local argument versus a global argument. All I've got on my paper right now is a local argument, just two separate points. So what we've got to do is take this one little step further. All right? I can say relative minimum at x equals 3, and here's the justification. Since, Matthew, you want to try this?
F prime of x from 0 is less than or equal to x, which is less than or equal to 3. What?
F prime of x,
Is less than 0.
okay, is less than 0.
I skipped that part.
Okay?
From 0, which is what? 0 less than x less than 3.
He's basically saying my derivative is negative for all x's from 0 to 3.
And then f prime of x is greater than 0.
Is greater than 0.
For x is greater than 3.
Okay. For x greater than 3. That is our global argument. That's my justification. I've got to say that I know that the derivative for every single x is negative on the interval 0, 3. Now whether you use that inequality notation or you actually say on the open interval 0, 3. All right. And f prime of x, or the derivative for every single x, is greater than 0 for all x is bigger than 3. That's your global argument. That's your justification, the way we want to phrase it. You know, this is work you did to convince yourself. This is the justification that we need to earn our AP points. The global argument.
So instead of the inequality symbols, we could use like the interval?
Yes.
Okay.
So instead of the inequality symbols, you could write, instead of this right here, you could say on the interval 0, 3. And instead of this right here, you could write on the interval 3 to infinity.
So
That would be fine.
what if you had a bracket between 3 and, like, could you use brackets instead, or would it be better just to stick with parentheses?
Well, now this is a good question. If I was asking, where is the function decreasing? I would say on the closed interval bracket 0, 3. Because my derivative is negative for every single x between here. But well, let's see. Now, I may not use the bracket on 0 because it just told me x greater than 0 in the problem, didn't it? Yeah, so I wouldn't use a bracket there, but let's just say in general.
But
if
you
I
would use it
knew,
on 3 other because it's not decreasing at.
well, no, that is a classic argument, JT. JT saying I wouldn't put a bracket on 3 either, because you say it's not decreasing at 3. At 3, the derivative is 0. That was a very divisive argument between AP readers the year I was there, and probably other years too. Half the group said yes, half the group said no. Here's the deal. If I am indeed decreasing on this entire interval, let's say the function had a value of 4 at x equals 0. And then the function at 3 over here was 1. And I have just convinced myself that I'm decreasing on this entire interval 0 to 3. Then what the proper way of saying it is indeed I'm decreasing on the entire, whoops, I don't want to show it like that. But I'm decreasing on the entire closed interval because the idea of definition of increasing and decreasing says for any small delta x I go over this way, that my function value here will indeed be less than the function value where I just was. And that will be true. It will be less than that y coordinate of 4. And it also says that I'm decreasing on the entire interval, that for any small delta x I go back this way. I'm exaggerating here with a big chunk of delta x. But it says that if I am decreasing, then this endpoint y coordinate will be smaller than the previous one I had. And that is true. So yeah, we're always going to show intervals of increasing and decreasing if I'm communicating that piece of information as a closed interval. Even though, yeah, at 3, my derivative wasn't positive, it was 0. But I include that in my intervals of increasing and decreasing. That was a tough one for me to swallow too. I wanted to be the other argument, but that was incorrect.
Bracket above these.
If I was communicating that, if it asked me on what interval is the function increasing, and if the prompt didn't say for x greater than 0 only, I think this one did, didn't it?
Yeah.
If it didn't say that, then I would have gone closed interval 0, 3.
It closed on the other 3.
Yes, sir. Yeah. And it's kind of bizarre to say, oh, I'm decreasing at 3 and I'm also increasing at 3. But likewise, if I said I'm increasing for all x is bigger than 3, then indeed, from 3 to any other x, that means this one is bigger than that one. And I have to have that one to compare to, you might say.
Okay, so would it technically be okay to do it either way, or would it just be safer?
Are they gonna count off?
Okay, do what either way?
Okay, say you're making an interval 0 to 3 and 3 to infinity.
Okay.
And 3 is both the point of increasing and decreasing, like they say, where you use a closed interval. Say you use an open interval instead. Would they take off for that, even if you had? Okay. That
Yeah.
sucks.
So you want to, for intervals of increasing and decreasing, you want it to be closed.
Okay.
Right. Now, for this justification, slightly different story. I didn't use closed here, did I? Because that's not what the question asked. The question asked me on what interval is the function increasing. This is my justification for a first derivative test. And that is saying that for all x's on this interval, my derivative changed from negative to positive. Therefore, at that critical number, I have a minimum. So this is the way I want to show it for a first derivative test justification. So what are they asking for? That's a big thing in the question. So now, this is the way I want to see it. The global argument f prime for all x on the entire interval. Now, you can phrase it different ways. I could say relative minimum at x equals 3 since the derivative changes from, yeah, I could say since the derivative changes from negative to positive at x equals 3. I could say that, and I'd be okay. Here's something I could not say. Now listen to this phrasing, all right? I couldn't say relative minimum at x equals 3 since it changes from negative to positive at x equals 3.
They won't know what it.
They won't know what it is, exactly.
They do, but they won't.
Am I talking about the derivative or am I talking about the function? Now me as the AP reader, I'm going to see this and I'm going to say, oh, I know they mean that the derivative is changing from negative to positive, but I can't make any assumptions. So you have to be very explicit. Don't use it. It is a bad word. All right? Because I don't know what the it is referring to. In fact, I believe in our packet, it might even, no, that's in a different little thing of teaching notes. But it talks about the use of the word it. Okay, so we've got that guy. Let's see. Oh, here we go. Let's take a look at, let's see, your second page of your packet. Turn to the second page of your packet real quick. And you're going to see some potential choices for how to phrase this. I'm going to get the projector back up here. All right. So these are some wrong answers. All right, they're kind of saying the right stuff, but no, not really good enough. This one person says, the function has a relative minimum at x equals 3 because the function decreases then increases. That's not good enough because it doesn't say where it decreased and increased. It's not specific enough. It doesn't communicate what it needs to communicate. So that's a bad way of phrasing it. SAT.
But they still got 1 point for that.
How did the scoring guide go?
I think it was just saying minimum of x equals 3 and then.
Okay, yeah, then, yeah, if that's the case, when you look at the scoring guide, yeah, by stating a minimum of x equals 3, you did earn one of the 2 points. But you're going to lose the justification point. Of course, that's what the focus of tonight's session is, writing good justifications. We want to earn that justification point, right? Okay. Person 2 here. And these probably are really and truly excerpts of what actual students wrote on the different exams. They'll pull those and show us. At x equals 3, the function has a relative minimum because the slope changes from negative to positive at x equals 3. Not good enough.
Why is it not good?
The slope of what?
The function. What if it said the function? Would that be right then?
Yeah, this doesn't say good, the slope of the function. And
Would that be good enough though?
Let's see what's wrong with number 3.
that would be better. But if we said the slope of the function,
That's a weird way to
Alright.
say it.
Well, no, it's
I don't get why
because it
number
doesn't say
three's
that it stops at 0.
number 3 says f has a relative minimum of 3 because the first derivative test shows the slope of f before x equals 3 is decreasing, and after 3 the slope of f is increasing. Well, that's just a flat lie. Because this is a very tricky thing about wording here. It says the slope of f is decreasing. And we don't know anything about the slope decreasing. That would be the derivative of the derivative being negative. What you wanted to say because f is decreasing, not the slope of f. They're getting, and I've seen this many times in when I read. They kind of double up on what they're trying to say.
Yeah.
And here it says the slope of f is increasing. But no, we want to say that f is increasing. Yes, sir.
I just want to do math.
Prime is increasing and decreasing.
But no, we didn't calculate the slope of f prime. If you said the value of f prime is positive, or the value of f prime is negative, that would communicate what we wanted to do. And that's what we said when I said f prime of x is greater than 0. That's communicating it. That, I think, is what you want to use. If we practice that. Now, in a different example, the student calculated the slope at x equals 2, so they used that for their first test value, and the slope at x equals 4 as their second, and wrote, since the value goes from negative to positive at x equals 3, or since it goes from negative to positive, x equals 3 is a relative minimum. Well,
Value of what?
yeah, the value of what? They don't say. Is that the value of the function? Is the value of the derivative? Now, they calculated it, but once again, that's the local and not the global argument. Now, and 5, of course, the classic error we said a moment ago, right? Hunter, what's wrong with 5?
It uses the word it.
It uses the word it.
It doesn't even say x equals 3.
Would it even get that first point?
Nope, number 5 would get 0. It doesn't say a relative minimum where. I don't think it would.
I think one at the bottom
Yeah.
is correct.
I mean, because it asks what x equals 3
Yeah,
was,
the
so-
prompt does say, at this point, does the function have a relative minimum, relative maximum? The fact that they've identified a minimum, they might still get that first point, because they did say at this point. So it's kind of obvious that they're talking about x equals 3. So they might have still gotten their first
Wouldn't it
point.
be considered a
It's
bald
like
answer though?
0.5.
Because it has no justification.
Well, they've given a justification, but it's just poorly written. Because it goes from negative to positive. They gave a justification. It just wasn't a good one. Because I don't know what the it is. Okay.
Not to be, I'm probably gonna do it.
Yeah, I know.
Okay, now, here-
To do. Oh, yes.
extremist. Now, this guy is another version of what a good answer could look like. For all x between 0 and 3, the derivative is negative, so the function is decreasing here. And for all x greater than 3, the derivative is positive, so the function is increasing here, therefore x equals 3 is a relative minimum. That would earn you a justification point because of the words for all x. That's the same as when we said f prime of x is greater than 0 or f prime of x is less than 0. That communicated the global answer. This communicates the global answer as well, as opposed to just calculating f prime of 2. Right? Okay. Another good solution. Now, you guys told me earlier we could do a first or a second derivative test. Another student actually calculated the second derivative and found that the second derivative of 3 was positive or greater than 0. And they wrote, by the second derivative test, x equals 3 is a minimum. When the second derivative is positive, f is concave up, so the extrema must be a minimum. That would suffice. That you've justified it using a second derivative test. That would work. The derivative of f changes from negative to positive at x equals 3, so this is a minimum. That would suffice also.
I like that.
Yeah, that one's pretty cut and dry. But you got to make sure you're very concise that the derivative is what's changing and where is it changing and how is it changing from positive or negative to positive. Okay. Now, in our packet here, it talks about these are just a template. If you memorize this way of phrasing it, you'll get the justification points every time. All right? It says the question of justifying an extreme value is asked so often that a template might be in order. So it says change the underlying parts as needed. So we just found a minimum. So, right here, this is what we saw in the scoring guidelines was a good answer. The derivative for all x is greater than 0 on my interval, and the derivative for all x is less than 0 on some other interval. Therefore, the function has a relative maximum at x equals b. And it says, just change with the appropriate sign and the appropriate word. Maybe if it changed from negative to positive, you would have a minimum. So just change those little parts to make it fit what you need to fit. This is a good template. That's the template we've talked about the most tonight. Here, and this is the one Nicole liked. The derivative of f changes from, you might say positive to negative if you want to show a relative maximum, or you could change this negative to positive at x equals b, so a minimum. Just note the phrasing of it. You're saying that the derivative is changing, how it's changing, where it's changing, and what it yields. I like the second and the third ways of doing it. The first one is kind of a combination of the two. These will get you your justification points. All right. Now these were for, if you remember the prompt, I think it asked for local. Yeah, and I said, this prompt says, does the function have a relative minimum, a relative maximum, or neither? So the tests for relative extrema are first or second derivative tests. When it asks for an absolute extrema, we have to change gears a little bit. So at the bottom of this page, you'll see absolute extreme values. For an absolute extrema, you must give an argument that includes the entire domain of the function, including the endpoints. So we have to look at the left endpoint and the right endpoint of a closed interval. Absolute extremas will occur on closed intervals only. All right, so they're going to limit your domain from being from 2 to 5. And you got to compare the y coordinate at every critical number with the y coordinates at 2 and at 5. All right. And as it says here, therefore, also the extreme value theorem, the endpoints are candidates for the absolute extrema and must be checked. So that's that candidates test. Okay, so let's take a look at whatever our next question is here. Okay, I believe 05 question 2 is our next one. Okay. As we look at this guy, tide
We're not
removed.
talking about the B and C on,
No,
Okay,
I was just focusing on the justification part tonight.
okay.
So the tide removes sand from Sandy Point Beach at a rate modeled by the function R given by R of t. Now, think about the phrasing. The tide removes sand from Sandy Point Beach at a rate. Oh. So I'm thinking R is the derivative of some function that gives me the amount of sand. So the integral of R would be the amount of sand, and the derivative, which is R, is going to be the rate at which sand is removed. All right? And a pumping station adds sand to the beach at a rate modeled by S. So that's how much sand is being blown or pumped back onto the beach. All right, so both of these are rates. Both R of t and S of t have units of cubic yards per hour. Right there is another dead giveaway that these are rate functions. They're the derivative of something. Because the units, cubic yards per hour. This, all right, here, units. This is the derivative of what? What does cubic yards calculate? Volume. This is the derivative or the rate of change of volume of sand. Units tell us right there. All right. It measured in hours from 0 to 6. Ooh, look. Including 0, including 6. They've given me a closed interval. All right. At time t equals 0, the beach contains 2,500 cubic yards of sand. There is an initial condition. Maybe I use that somewhere along the line to find my plus c that Brenda told us about earlier from the previous question. All right. Now, as we look through this guy, let's talk through parts A, B, and C. Part D is what we're wanting to focus on, the justify your answer. Well, let's talk through A, B, and C. How much sand will the tide remove from the beach during this 6-hour period? Indicate units of measure. Well, this we need to make sure and talk about tonight too. Alrighty.
This is with calculator, right?
This is question 2. This is with
So
calculator.
you can
Absolutely.
do the first part on your
Right.
calculator.
Yeah, the first part is definitely a calculator. You got to show the setup and then the answer round to 3 decimal places. So if I want to calculate how much sand was removed, I've got to think about the total volume of sand. Well, again, this was the rate of sand removed. If I integrate the rate function, I get the volume function. So on the 6-hour period, it's going to be the integral from 0 to 6 of R of t dt. Put R of t in your y1 in your calculator. Second, calculate the integral from 0 to 6. Boom. You'll get the 31.815 or 816. Yes, sir.
How did adding the units of measurement cause it to gain another decimal? Like what?
Oh, it didn't gain another decimal.
Well, like why did it change?
This is rounding.
Okay.
The answer was